Alrighty. This goes hand in hand with talking about balancing equations. Um, and it's going to kind of get us warmed up for um, talking about reactions and learning to predict products and that kind of stuff. And that is seeing the patterns in some common reaction patterns. Okay. There's a handful of common patterns, and we're going to look at them. And we're going to start eventually building ourselves up to predicting products and looking at how reactions work and all that kind of fun stuff. All right. So this is, getting our feet wet as we talk about stuff. All right. Um, combination reactions. Combination reactions are easy to spot because we're taking multiple reactants and literally combining them together into new things. Okay. So here we're taking an ammonia and an HCl and we've made ammonium chloride. Or we can take nitrogen and hydrogen and make ammonia. This is a great reaction down here because we can take aluminum and liquid bromine and we'll make aluminum bromide, which just writing it out doesn't look like it's super exciting. But when you do it, you literally were taking, oh, excuse me, um, you have liquid bromine in your tube down here. You can see the brown liquid is kind of shooting all over the place. We're getting sparks. And what they're doing is they're dropping a piece of aluminum foil in there. So you can just drop aluminum foil into the bromine and the cloud, the smoke that's coming out is aluminum bromide, um, the product. It's kind of powdery and it kind of goes everywhere. And the sparks are because this reaction just gives off a lot of heat. So it's a really cool looking reaction, but it counts as a combination because we're taking two things and combining them together to make one. Okay. The opposite of this is my pen's going crazy. Okay. The opposite of this is called a decomposition. Okay. Where you have two or more products are formed from a single reactant. So this is something coming apart into other pieces. So one of those is what this guy's doing here is elephant's toothpaste demo, where he's using hydrogen peroxide decomposition and soap bubbles to make this fun little thing squirt out. I shouldn't say little, he's got a big one going there. Um, anyway, what he's doing is he's got hydrogen peroxide here, um, and what's happening is slowly over time, the peroxide decomposes to give us not hydrogen, excuse me, water and oxygen gas. And um, he's adding a catalyst to it when he does it so that the soap bubbles catch the oxygen and makes this nice tube of foam. Um, it's cool. The catalyst makes it go a lot faster, but it's still the decomposition reaction. Um, Here we can have calcium carbonate. When you heat it up, I probably should have put a heated up symbol on this. Will revert to calcium oxide and give off CO2 gas. This is a decomposition reaction as well. There's also a really fun one. I'm going to let you guys go look this up. This is ammonium dichromate. Um, and you can actually make what's called an ammonium dichromate volcano. I say look this up. This is a YouTube link for a nice video demo. I used to do this, but I don't like the chromium stuff because it's kind of toxic. So I don't really want us breathing that in because it makes a nice flumy mess. You get a nice color change. I'll let you look at that. This link is on our Blackboard page, so you can click that and see what it is. But it counts as a decomposition, and it's pretty violent too. We get the nitrogen gas, the water actually comes off as gas, and we make the chromium oxide, um, chromium 3 oxide as we do that. Okay. Let's see, what's our other one? The other one, we're going to spend a little bit of time on the other one, more time maybe. And that's a combustion reaction. And a combustion reaction, um, essentially, what we're thinking about is our broadest definition possible for a combustion reaction is we're reacting with oxygen. Um, Literally, what we want to think about here, though, is we're limiting ourselves to think about something that's an organic compound that's burning with oxygen. Okay. Um, and this can happen lots of ways. You get a lot of mixtures of products when you do this. Um, if you let the reaction go completely, okay, and you get everything fully combusted, you have what's called complete combustion. And complete combustion is nice because you only get water and CO2 out as products. Okay. Um, that's kind of a little bit of a fib, and we'll talk about that in a second. Um, but really, this is also stepping up to giving us um, another balancing idea when we do this. Okay, but yeah, um, organic compounds are like this is like fuels, like when we do our Bunsen burner in the lab, or you're doing gasoline in your car to come. These are all combustion reactions to do that. Okay. So let's look at this. The first one here we're looking at, this is C4H10. This is butane. I don't care if we know the name. When you get into organic chemistry, I will care if you know the name, but for right now, we're not going to worry about it. But we're combusting butane and we're doing it completely. So we get carbon dioxide and we get water gas out. Okay. Notice here, the water is coming off as a gas because this thing gives off a lot of heat, right? You can see it here when the person lights this thing on fire, the fire is releasing the heat from the reaction. All right. So we want to follow our same kind of ideas when we're balancing stuff. We're going to start with the butane because there's where our biggest subscripts are. So we have 4 carbons. So we're going to put a 4 here because now we have 4 carbons. We have 10 hydrogens. So we're going to put a 5 here because now we'll have 10 hydrogens. Then we just have to pay attention to the oxygens. How many oxygens do we have on the right side? Well, we have 4 times 2. This is 8. And we have 5 times 1. So this is 5. So we have, what is this? 13 oxygens on the right side. And we have 2 oxygens on the left side. There's not a good way to do this. Okay. But we can still balance it. You can think of this as if we had 13 halves of O2, we would have 13 oxygen atoms, and that would balance it out. But we can't have fractions in our balanced equation. So instead of doing that, what we're going to do is we're going to multiply this by 2. And when we do that, we're going to get 13. Okay. So if we put a 13 here and double everything else, so 2 butanes, change this 4 to an 8, and change this 5 to a 10, now it's balanced. This is a trick that's going to work for any combustion reaction you want. Okay, the oxygen being diatomic is going to throw us off. So if your product side has an odd number of hydrogens, slap that odd number on the oxygen on the left and double everything else you've already done, and it should be balanced. Okay, you can always check yourself. Let's do this other one. If oxygen is present, you still have the organic compound. Um, right, there's an oxygen in our organic compound that we're combusting. Um, but we can balance it the same way. You're still going to get CO2 and water as products. All right, so let's do this again. 4 carbons, 4 carbons, 10 hydrogens. So we need 10 hydrogens, so we're going to get 5 waters over here. Now we're going to count oxygens. We've got 8. It's the same as up there. I don't know why I'm waffling here. Okay, the right side has 13. This is 2. And this is 1. Now, this is nicer because we can say, okay, remember we have 1 right here. So if we take 1 away from this, we get 12. 12 oxygen is easy to balance because we just need 6 of those. Now 6 times 2 gives us 12, plus 1 more gives us 13, and now we're balanced. There's no weird doubling in there. Just pay attention. Don't forget that there's oxygens there when you get there because sometimes we forget. Okay, just pay attention. Double check when you're done at the end. Okay. You can also remember, you can also have organic compounds that have things like sulfur or nitrogen in them, and they work the same way. Okay. The complete combustion is going to give you CO2 and water. And I forgot to add this, so we're going to add it right now while we're thinking about it. But if you have a nitrogen there, we're going to get NO2. So I'm going to add NO2. I should have had this typed on there, but I didn't. Okay. And we can balance it the same way. We're just going to have a lot more to deal with as we do it. Okay. So 4 carbons, 4 carbons. 9 nitrogens? Ooh, that's not nitrogens, that's hydrogens. How is that not going to balance? Oh, it should. We just need 2 of these. So we can get 8 there. This is what I get for making up examples and not working them out first. That's 8 carbons. That's 18 hydrogens. So we want 9 waters there. Okay. That gives us 2 nitrogens. Where'd my 2 go? There it is. 2 nitrogens. And now we just have to add up our oxygens because we only have 2 on this side. 8 times 2, that's 16. We have 9. And 2 times 2 is 4. Why did I make this math so hard? This is 29 oxygens on this side. 29 oxygens over here. All right. So now we have an odd number and we have O2. So what we're going to do is what we did a minute ago, and we're going to slap the 29 right here and double everything else. So that's now a 4. That's now a 16. That's now an 18. And this is now a 4. 4. And it's balanced. The coefficients are bonkers, but it's balanced. Okay. And because we have a 29 in there, um, those are the lowest whole numbers possible. Okay. We do the same idea with sulfur. Hopefully, it's not as bonkers as um, what we just did. But if we have sulfur in the mix, we're going to get SO2. So let's add an SO2 over there because I forgot to type it in there. SO2 gas. All right. Um, all right. Now let's balance this guy. 5 carbons, 5 carbons, 12 hydrogens, 12 hydrogens, right? Same kind of idea as we're going. Let's see what's left. Sulfur, we got 1 sulfur here, we got 1 sulfur there, so we're okay. Now let's count some oxygens. 5 times 2 is 10. 6 times 1 is 6, and 2 more. Oh, great. This is 18. That's an even number we can work with, so we need 9 of those O2s, and now that dude's balanced. I didn't give myself a check mark on this one. I feel bad. There we go. All right. Hopefully this makes sense. I just want us to recognize what our patterns are as we're doing stuff, okay? Combination is adding things together. 2 things on the left, making 1 thing on the right. Decomposition is decomposition is the reverse of that. 1 thing on the left, making 2 things on the right. Combustion is making carbon dioxide and water. So you could expect to see questions like, okay, here's this organic compound with a formula, write a balanced equation for the complete combustion of whatever that formula is. You can do that. Complete combustion is CO2 gas, water gas, and if you have nitrogen or sulfur, you're going to need NO2 gas or SO2 gas. All right. If you need me, let me know. Um, I'm here to help, and I'll see you in class.